So I mentioned when I was handing this out that this is the second of the quadratics unit, and I've mentioned in the past that in Math 10, most of the mathematics in Math 10C is focused around what we would call linear mathematics. The equations are linear, the functions are linear. You see equations in Math 10C like that. That happens to be called a linear equation. The reason it's linear, and I don't know if you recall this from Math 10, is that the exponent on your variable is 1. And what that means is that there's going to be one solution to the equation. If you were to solve that equation, you're going to get one solution. And I don't know if that was really pointed out to you or not. We can certainly solve it. I would add 5 to both sides and get 3 times x plus 2 equals 17. You could multiply this out. Most of you were probably taught to do that. There's other ways that you could find x from this middle line, but you could multiply it out. Then you would subtract 6 and get 3x equals 11. And then when you divide both sides by 3, you get x is equal to 11 over 3. Unless I've made some kind of careless mistake, which I'd like you to just double check, that's what I get. I get one solution. I don't care how many times you rearrange that equation, you're going to get one solution. Linear equations have one solution. That's an equation. This is called a linear equation. And I'm not going over the history of mathematics here just because it's interesting. It's the terminology that's very important here. This is a linear equation. On the other hand, last year as well, you study what are called linear functions. And we have a lot of people teaching Math 10C in the building, and everybody has their own little take on things, but I hope you remember that there's a difference between a function and an equation. A linear function is an equation. It does have an equal sign, but it also has another variable. This is an example of a linear function. Y is equal to negative 2x plus 5. That's a linear function. So I just want to highlight that for you to illustrate, first of all, the difference between a function and an equation. And if you give me a minute, I have to bring something back. I've lost a program that should be running in the background. I just want to highlight this for you, that a linear function, this is an example of a linear function. Whereas what I talked about before, a linear equation, this is an example of a linear equation. And the basic difference is that one of them has x in it and the other one has x related to y. We don't have to have x in an equation. We could have the letter a as something we're solving for. And you certainly don't have to have a linear function that has y and x. It could be a and b or p and q. In other words, the variables could be p and q. I'm not talking about parameters here. I'm just saying the letters that are the variables in a function could be anything that we desire. For example, on the exam you did yesterday, you created a function where x was the horizontal variable, but your y was actually revenue. Most of you did the revenue problem, right? Some of you did area is the vertical axis and x is the horizontal. But the point is you could use whatever variables you want. There's a reason why this is a linear function. And it's because if you were to sketch this function, and you should probably remember from last year that the slope is equal to negative 2 and the y-intercept is equal to 5. Does that vaguely ring a bell? Y equals mx plus b. You should know that this graph of this linear function has a slope of negative 2 and it passes through y equals 5 on the x-axis. Well, it's not called linear for no reason. The graph is a line. Okay, it's a linear graph. And I want to point out to you that it has one x-intercept. It has one x-intercept. A linear equation has one solution. A linear function has one x-intercept. Okay, well, we just spent the past couple of weeks talking about quadratic functions. And what I'm trying to do here is give you a very broad understanding of where we're going and where we've been, all the way from Math 10C to where we left off at the end of this last unit, leading into what we're going to be doing for the next couple of weeks of classes. A quadratic function, we know a quadratic function, and I'm not going to write out the general form. I'm just going to give you one. Negative 2x squared plus 3x minus 12 is a quadratic function, correct? Okay. I'm going to change this to plus 12 just to be sure about something. If we were to sketch a graph of that, we could use our skills of completing the square. But I've chosen a number here for b of 3, which makes it awkward when you factor that negative 2 out. You're going to be dealing with fractions. Just to drive my point home, let's just take a look at this on a graphing calculator. What does negative 2x squared plus 3x plus 12 look like? By the way, it's a function. It's a function because there's y and x in it. It's quadratic because this is the form that quadratic functions take. Whereas linear is just x to the 1, quadratic has an x to the 2. I want to actually just pause there for a second. Quadratic has an x to the 2. Is this still a quadratic function? Yes, it is. It doesn't have to have an x to the 1. But the highest exponent, which we call degree, the highest exponent in a quadratic has to be 2. By the way, if the highest exponent were 3, there's a name for that called cubic, which we learn about next year. And next year you learn about quartic, which is degree 4, and quintic, which is degree 5, and degree 6 and degree 7, and we expand our horizons next year to all these. But this is quadratic in nature because it has a highest exponent of 2. Now, where was I? I was going to graph this on the graphing calculator so that I can talk about, a linear function and what the graph of that looks like, and a quadratic function and what the graph of that looks like. We know what this looks like, don't we? Roughly speaking, you know that it's a parabola that opens down. It has a maximum, but, and I hope I chose numbers that work. If not, I might have to change them. Negative 2x squared plus 3x plus 12. I'm just going to choose to go zoom 6 because that's usually what we end up doing. Zoom standard, and we can, if we need to see more detail, we can change our minds and adjust it later. I am going to adjust it. I've got a lot of room on the left and the right that's wasted, and I don't quite see the vertex up top. So I'm going to start at negative 5 and go to 5 for x, and I'm going to go higher for y. And I hope that over the past couple of units you've gotten more and more used to adjusting those window settings. But here is my point. The reason why this is a linear function is because the highest exponent on x is 1, and there's one x-intercept. The reason why this is a quadratic function is the highest exponent on x is 2, and there's two x-intercepts. Now we know, of course, it gets a little messy. It's not a golden rule because we know quadratic functions could have no x-intercepts, couldn't they? If this parabola were entirely below the x-axis, it wouldn't touch the x-axis. We also know that it's possible to get a quadratic function that has one x-intercept. Who can tell me what a quadratic function that has one x-intercept would be like? Like, how is that possible? Ashira? Right, when the vertex is on the x-axis, so there's no parameter of q. Q is 0. It's not been shifted from the origin up or down. It may have been shifted left or right. So quadratic functions can have no solutions, no x-intercepts, It can have one x-intercept or it can have two x-intercepts. Now, with a linear function has to have one x-intercept. You cannot have a linear function unless it crosses the x-axis. Okay? But here's a point I want to make right now before we finally get started with the lesson. This linear function has to have one x-intercept. A linear equation has to have one solution. There's one exception to that, but I don't want to confuse you with it. A quadratic function can have two x-intercepts, or it can have one x-intercept, or if it can have no x-intercepts. If you look at the title of this unit that we're dealing with is quadratic equations. So we are going to be dealing with things like, well, we can look at the examples. We're not going to do the examples right now. But this is an example of a quadratic equation, not a quadratic function, because it's not equal to y. It's an equation that has a variable we could solve for somehow. And since quadratic functions can have no x-intercepts, some quadratic equations don't have any solutions. Since quadratic functions can have one x-intercept, quadratic equations might have one solution. And some quadratic functions have two x-intercepts, which means there must be some quadratic equations that have two. And you need to choose the words function and equation carefully. When you're talking about what's on the screen here, that's a quadratic equation. If you saw a similar quadratic expression, but there was a y involved as well, that's a quadratic function. So all that being said, let's look at this formally now. This is on, page 1 of the unit handout, because it's a brand new handout. And that formula that's on the cover page where it says, "Behold the wonder of the quadratic formula," it's called the quadratic formula, not a quadratic equation, is something that we're going to learn about after about 5 or 6 days of lessons in this unit. So this is 4.1 in your textbook. And terminology, first of all, we already know that that's called a quadratic function. There's nothing new about that. And quite frankly, at this point in time, you can forget entirely for a little while about vertex form. Okay? We want standard form. So that is a quadratic function in standard form. Remember that standard form is y equals ax squared plus bx plus c. You should be able to see that a is 1, b is -1, and c is -6. That should be obvious. If you don't know what I'm talking about, then you must have slept through the entire last unit. Okay? However, this is called a quadratic equation. And I've chosen an example here for an equation that kind of parallels the example I have for a function. They both contain the quadratic polynomial or quadratic expression x squared minus x minus 6. They both have that quadratic expression in it. But because in one, the one on the right, it's equal to 0, it's an equation, and there are values of x that make it true. Maybe. Maybe there's one value of x that makes it true, maybe there's two values of x that make it true, or maybe there aren't any values of x that make it true. On the other hand, the one on the left is called a quadratic function. And I can understand why a student here would go, what's the big deal? It's just a word. I think you know me by now as a teacher. I don't try to stress something unless it's going to make you more successful at math. If it were just a matter of terminology, I probably wouldn't even talk about it in any real detail. It's important. To solve an equation, now there's some more terminology here, means to find the values of x that make the equation true. So I'm going to go back and talk about this equation right here. The one that's highlighted, and we got x equals 11/3. Well, if I were to take that original equation, 3 times x plus 2 minus 5 equals 12, and I put in for x the solution that I got, which is 11/3, I would like everybody to use your calculator and calculate what the left-hand side of that is equal to. You're going to start in the brackets. You're going to take 11/3 times plus 2. Then you can multiply whatever you get by 3, and then you can subtract 5 from it. Is this a 17? Is that what I had originally? 12. Just a second here. I'm going to have to fix that. I changed it to 17. Oh, because I added the 5. That's why. That's why. Okay. So this is a 12. It's unfortunate that my 2 kind of looked like a 7 there. It's not 17, it's 12. I'm looking at the original equation. Are we in agreement that when you calculate the left-hand side, you get 12? Okay. Well, what we write in math, and we're going to be doing this a lot in the next couple of weeks of classes in my 30-1 class, is we make a statement that the left side equals the right side. In other words, that solution is the value of x that makes it true. And going back to my notes here, to solve an equation means to find the value for the variable that makes the equation true. We call that value the solution, but we also call it the root of the equation. So if I say to you, find the solutions, or find the solution to this equation in yellow, the solution is 11 over 3. If I say determine the root of that equation, the root is 11 over 3. Root is another word for solution. Okay? The solutions to an equation are called the roots of the equation. So we have a warm-up here. We're going to use our graphing calculator, and we've had lots of practice with this, to determine the x-intercepts of this function y equals x squared minus x minus 6. So you're going to enter for y x squared minus x minus 6. Let's just start off all on the same page and go zoom standard. That's what it looks like. I am going to shave off a bit of the left and right side to kind of broaden out the parabola a bit, scale-wise. I'm going to start at -4. I got to look at it again. I'm going to start at -4 and go up to 5 for x. Now, a big part of today's lesson, by the way, is some theory that we need to understand, but also a big part is understanding your graphing calculator even more than we did in the past. Remember, when you go to the window setting, if the scale is 1, that means there's a tick every 1. So when you look at this, you suspect looking at the graph, but you're not sure, that there's an x-intercept of -2 and an x-intercept of +3, correct? That's what it looks like. You could confirm it, I suppose, by going to your table, making sure independent says ask, and put in -2 for x. You get a y coordinate of 0, which means it's on the x-axis. It's an x-intercept. You could put in, what was the other one, 3, and you get that. But if it wasn't obvious what they are, then you go to your calculate menu and choose 0. Remember that 0 is another word for x-intercept, and I want to pause there. When you're dealing with a function, we use words like x-intercept or 0. Those are words that talk about properties of a function, of a graph, and we'll come back to that in a bit. But you go to your calculate menu, you choose 0, you scroll, or you enter a value. I'll put -3 for x that's to the left of the x-intercept of interest. You then hit enter and put in or scroll to an x value that's to the right, and then you hit enter a third time, and it tells you what it is. So definitely an x-intercept of -2. And if you were to do the same thing, and I know you know how to do this, but just for completeness sake, I'm going to do it anyway. Put your cursor to the left of that, and then put it to the right of that, and hit enter. And you get the other x-intercept, which happens to be 3. Are we fine with that? Any questions with that? All right. Second part of the warm-up. Substitute the value for the x-intercept into the quadratic equation that's listed here in number 2. In number 1, it gave you a quadratic function. In number 2, it gives you a quadratic equation. And one of our x-intercepts was -2, and one was +3. So what we're going to do is put -2 into x squared minus x minus 6 equals 0. And I want you, when you write this down, not to put an equals there. Because what we're about to do is verify whether -2 makes the equation true or not. And it might seem like a really picky thing, but when you're trying to find out if a value for the variable makes it true, you can't assume it's equal from the beginning. You leave the equals out of it. If you come to the conclusion that it's equal, then you can say, yeah, they were equal. So I'm going to put -2 in for x. Of course, you put it in brackets. You don't need to put it in brackets necessarily everywhere or all the time. But if you do, you can't make a mistake. Well, if you do, you'll make fewer mistakes. I simplify this. -2 squared is 4 plus 2, because minus -2 is plus 2, minus 6. I get 6 minus 6. I get 0. So we conclude that the left side is equal to the right side. If we do that with 3, again, we have x squared. We have x squared minus x minus 6. We're going to calculate what that is when x is 3 and see if it makes the equation true. So that's 3 squared minus 3 minus 6. That's 9 minus 3 minus 6, which is 0. So again, the left side equals the right side. Let me summarize what this is telling us. I want you to notice that this that's equal to 0 in the equation is the same thing that is equal to y in the function. I'm choosing it this way intentionally. So what we have learned, or apparently learned, is that if you have a function of y equals f of x, and you have an equation of f of x equals 0. So whatever y is equal to is the exact same thing that's equal to 0 in the equation. That the x-intercepts, or zeros, are the same as the solutions or roots. We got an x-intercept of -2. That happens to be a solution to the corresponding equation. We got an x-intercept of 3. That happens to be a solution to the corresponding equation. It's always going to be that way, by the way. But why? Why should this thing that you're looking at on the board be true? There is a reason, and we're going to explain it. It's a very simple explanation, but I want to see if anybody can land on it on their own. Just give you a minute to think about that. Ashira?
Is it because, like, y equals that f of x and f of x equals 0, then the y coordinate has to be 0, and so you're on the x.
That is exactly it. How is it you find x-intercepts? Forget about all this talk of equations and functions and all that. How is it you find x-intercepts? Even last year, I'm going to go back in time a little bit here. I gave you, as an example of a linear function, this highlighted blue function. If I said to you last year, what is the x-intercept? You would say, well, any point on the x-axis always has a y value of 0. And this is what you're taught, even back in grade 9, I believe, that you take this and you go 0 equals negative 2x plus 5. I don't care what the solution to this equation is. I don't care what the number is, but it's going to be the x-intercept because you've changed y to 0. So essentially, we can summarize this by saying that if y equals f of x and x-intercepts are where y equals 0, which, and I'm just not even really paraphrasing what you said, I'm just saying it in my own words. You said the same thing. If y equals f of x and the x-intercepts are where y is 0, then 0 equals f of x leads to the x-intercepts. The solutions to that equation have to be the x-intercept of the corresponding function. And I want to, this lesson is not a very deep lesson, but I want to demonstrate something to you that's very important for every unit forward now, every unit forward. If I ask you to solve the following equation, log of x, which you don't even know what that means, okay? I'm going to get to it in a second, equals 10. No, better not go 10. Equals 2. And I say solve that equation. You have no idea how to solve that equation. You don't, okay? Because you don't know what log, I'm going to actually change this to 1.2. Okay, I'm just thinking ahead about what this is going to look like. You don't know how to solve that. You're trying to find a number, and I'm not going to explain what log means, but there's a log button on your calculator. So maybe x is 3. Log 3. No. Maybe x is 20. Ooh, close. There's some value of x that makes that true. So you can solve this without even knowing what this log key does by doing the following. Make an equation out of it that's equal to 0. And then say, even though there was no y there, I'm going to graph log of x minus 1.2, and I'm going to find an x-intercept of that graph. And the x-intercept of that graph is going to be the solution to that equation. Let's try it. And I've changed some numbers here so that we get a little bit more practice with your window settings. Log of x, you need to close the brackets on that x, minus 1.2, and we go graph. And now don't worry about why it looks like what it looks like. That graph is curving up closer to the x-axis. Is it going to reach the x-axis? Probably. So let's look in that direction. Let's change our window setting to go up to 15. Looks like I have to go maybe a little further. And I also am going to shave off the top and bottom of my view window here. So I'm going to go up to 30, and I'm going to start at -2 and go up to 2. Can you find that x-intercept? Is it possible? Sure. Go to your calculate menu, choose 0. Put your cursor to the left of it, hit enter, put your cursor to the right of it, hit enter, hit enter. So this number that says x is the solution to that equation. I want to just make a couple of points. I'm always a little baffled by the fact that students don't remember this idea. Because, for example, in Math 30, if we're solving a trig equation and you forget how to solve a trig equation on paper, you can solve it on your graphing calculator. can solve any equation on your graphing calculator. By the way, the other thing I want to show you is if I quit out of here and I hit my X key from the home screen, there's the X value. What is the log of this supposed to give us? 1.2. Now, I admit it, you don't understand anything about logarithms, okay? And I don't want to explain it. But this idea is true whether it's quadratic or linear or trigonometric or logarithmic or exponential or rational or radical or anything. So that is what we're doing today. We're going to solve these quadratic equations graphically. Do you remember when we found coordinates of vertices graphically, and some of you said, I don't like it? And I said, well, we're going to learn very shortly how to do it algebraically. I can probably solve this algebraically a lot quicker than you can do it graphically, and so can you if I taught you how. We will learn the algebraic methods later. So, what do? We graph this equation. That's all we do. We graph the equation, we find the x-intercepts. The x-intercepts of that, I misspoke. You probably didn't even notice, but I said we graph the equation. We graph the function, the corresponding function of the equation. Find the x-intercepts of the function, and those will be the solutions to the equation. So what I've done, all of the learning and new material has already been taken care of here. Now it's just a matter of putting it into practice. You know by now sometimes, you've seen me do that before, right, with x squared. Just go xx. I don't know why I do it. Zoom 6. Let's go back to Zoom 6. Ooh. Okay, so we're going to learn another feature of your calculator that I don't know that I've shown you. Do you agree trying to zoom in on that little area there to investigate what the graph is doing by changing the window settings is a little bit tricky? Go zoom box. Have you seen this before? What I have now is a little blinky cursor, and I'm going to put it kind of a little bit to the left and below that area of interest. And I'm going to hit enter, and then it's like a piece of elastic or stretchy, sticky gum or something that I can stretch out into a rectangle. And when I hit enter the second time, my calculator is going to use the minimum and maximum x as being the left and the right of the rectangle, and it's going to use the top and the bottom as my y boundaries. And then I can worry about going to my 0 in the calculate menu. Let's do the one on the left first. (1.3) repeating. I don't want to get waylaid or sidetracked rather into talk about fractions here. If you don't know that that's 4/3, quit out of here. Hit X. As soon as it said X equals, it stores it temporarily as X. And then go math, enter, enter. It's 4/3. Okay. Do me a favor and find the other x-intercept and confirm that it's 2. Some of you already have. Can I get anybody else to confirm? I know I only just saw a couple people. Yeah, Paige, you have it as well. So what that means, and I want to be very careful here, this would never, ever be a written response question. But if I asked for an adequate explanation, what you've written is not answering the question. The question is, what are the solutions to the equation? In fact, there wasn't even a y in the question. The solutions are x equals 4/3. And x equals 2. Those are solutions. We don't even refer to them as x-intercepts, that's all. (8p squared plus 18p minus 5 equals 0. Well, we're going to do this. There's no y, so we're just going to make it y because it's equal to 0. There's no x, but I mean, I hope you learned, and understand that we can transfer that equation into an equation for x, and if we solve that equation, we're finding p. Be very careful here when we write our answers. Don't write x equals, write p equals. All right, what do we have? 8p squared, so 8x squared plus 18x minus 5, zoom 6. Always double check your entry before you commit yourself to the graph. I hope everybody understands that this x-intercept here is on a part of the graph that's very steep. So when you try to put your cursor to the left and to the right of it, it's precarious. You're going to move your cursor a little bit and it's just going to take off the screen. So it's probably better to adjust the window settings. I can see by the looks on some of your faces that some of you didn't bother to do that and you still get the answers. Doesn't matter. I like a more complete picture of the graph. And we're going to find out what these are. I'm guessing, has anybody have them already? No? Okay, we'll get working on it then. I don't think it's 1/5, is it? This one, I was just guessing by looking at it, is -5/2 for the first x-intercept. If you want to know how I know -2.5 is -5/2, I just know it. If you want to convert it to a fraction, that's fine on your calculator. My other x-intercept is 0.25, which is 1/4. Any questions with B? All right. What do we have to do here? Well, it's not equal to 0. So what I'm doing here is something that I'm going to tell you from this day forward. There's always going to be exceptions. There's going to be times in Math 30 where I'll say, remember I told you this? Well, we don't want to do it here. But from this day forward, as far as we're concerned, generally speaking, to solve any quadratic equation, the equation must be zeroed. It has to be set equal to 0. Even when we solve it using algebraic methods, we have to set it equal to 0. So now you're going to graph this. I'm going to write down in a different color that you are graphing this, but from here on for the rest of the lesson, I'm not going to write that anymore. You should know you're just graphing y equals, you're finding the x-intercepts. So I would like you to determine the solutions to this equation. By the way, when I went zoom standard, this is a perfect situation that zoom box can be used. You don't need the vertex, I just like to see it in my picture of the graph. How many of you have the two x-intercepts already? Is one of them -1, Aoki? So I'm not even going to write x-intercepts. I'm just going to go up to the equation and say x equals -1. And I'm going by a little bit of knowledge of the algebra here, but when you find the other one, Aoki, do you get positive 0.22222, which is positive 2/9? Okay. For x squared minus 20x plus 25 equals 0. I mean, we have to zero the equation. You can't graph something to find out the x-intercepts unless you're equating it to 0 because y is equal to 0 for x-intercepts. So, in order for me to get the equation to be equal to 0, I can either move all of the terms to the left side, which I have chosen to do, or I can move all of the terms to the right side. My advice is always arrange it so that your quadratic term, your term that has x squared, is positive. You could move everything to the other side and have negative 4x squared plus 20x minus 25 equals 0. You'd still get the same x-intercepts. I know what's going to happen here. I would like you to graph it on your calculator and see if you can wrap your head around what you're looking at. And I'm not going to spend a lot of time talking about this one, but if you zoom in on that, I'll use zoom box again. It appears as though it's touching the x-axis at that point, but do you agree that due to the limitations of your graphing calculator, maybe it goes below it and then back up? I'll tell you this right now. If you continue to zoom in more and more and more, it won't happen. Okay? So there is only going to be one solution because there's only one x-intercept. You will learn later, the first day back after spring break, how we can look at this algebraically and see that there's in fact only one solution. But that solution, this should still work. I can't remember if it will or not. Even though it doesn't cross the x-axis. Enter. I'm pretty sure. Yep. And we've encountered that before, right? Where it's 2.49999. Like your intuition says, I think the calculator is just glitching there. It's 2.5, which is 5 over 2. I do have to say this, and you can laugh if you like, but I actually, over 30 years of teaching, I've had 2 students who were under a misconception here. And the first time the student asked me about it, I thought maybe they were pulling my leg and having fun, but they sincerely thought this was the case. X equals 2.5, and that's 5 over 2. Would you agree? This student thought that. Okay? And it is kind of funny when you really think about it, and I'm not poking fun of anybody who might believe that that's to be true. 2.5 is not 5 over 2 because there's a 5 and a 2 in 2.5. 5 over 2 just happens to be 2.5, okay? It doesn't always work that way. That's not true, in other words, right? This is not true. All right, let's try another one. Solve each quadratic equation. This time we're going to go to 2 decimal places because all of the answers to question 1 were rational numbers. They could be expressed as fractions. These will not be. These are going to be decimals that you cannot convert to a fraction. So y is equal to 2x squared minus 10x minus 9. Do you see what I've done there? I've automatically said y is equal to. There is no y. This is all going on in my head. Zoom 6. Ooh, that's interesting. I'm glad I did that. How many of you have ever graphed something on your calculator and all of a sudden you see those dots in the top right corner dancing around and nothing's graphing. For years, I thought the calculator locked up, so I would turn my calculator on and off. When you hit enter while it's in the process of graphing, it pauses the graph. So when I hit graph and then I hit enter right away, it paused the graph. Just to unpause it, do that. Can you do me a favor and to 2 decimal places, the nearest hundredth, find the values for the x-intercepts there, and we'll compare our answers. Well, you will compare your answers to some other people. I'm not going to actually do it. Hey, okay, you're lightning quick on your calculator. Can you tell me what the negative x-intercept is? Negative 0.78, which means the solution is about negative 0.78 for x. And we put a little dot above the equal sign to indicate that it's about. And can you tell me the one on the right? 5.78. It's kind of interesting that they have the same decimals, and unless I'm mistaken, they have the exact same decimals. I don't know if you noticed, but the decimals are exactly the same, which is an interesting idea. 5.78. I think you get the idea. We're just going to do one more here and then finish off with the final examples. Go ahead and solve this for me graphically. You're solving this quadratic equation graphically. What do you think, Owen? Not sure, eh? Okay. Well, that's fine. How many of you know what the answer to this question is? Jay, what do you think? The graph is above the x-axis, and by that you mean entirely above the x-axis. It's a parabola that opens up with its vertex above the x-axis. So there are no x-intercepts. So what does that mean about this equation we're trying to solve? There's no solutions. This equation doesn't have any solutions. We had an equation that had 2 solutions earlier. We had a few of them. You've had an equation that has 1 solution because it's just the vertex is on the x-axis. This has no solution. There will be a way when we return after a few more days of class, probably about the 4th day back, where we will learn how you can look at that and tell whether it has no solutions, 1 solution, or 2 solutions. Which brings us to, let's just skip over C and D, you get the idea. What are the 3 different situations that can happen with a quadratic equation? You can have no solutions, no roots, 1 root, or 2 roots. And all of this up here, I'm talking about an equation. Okay? What I'm going to draw below is about graphs or functions. So if there are no roots, what that means is the quadratic function that corresponds to the equation will look something like that, or it will look like the one you just did that opens up with its vertex above the x-axis. If there is 1 root, then it will look like that example we just did a couple back, whether it's at that point or whether it's to the left of the origin, or whether it's opening down. The important part is the vertex is at the origin. And if there are two roots, of course, what that means, if there are two roots or two solutions, there must be two x-intercepts, so that's what the corresponding function will look like. All right. One last question to do. Two numbers have a sum of 46 and a product of 396.75. This question is not just about getting the answer. Okay, there's a lot of math in this. So we're going to solve an equation, but we need to define variables. We're going to let x equal one of the numbers. There's other ways we can do it. We don't have to use x, but I like x. What is the other number then? If x is one of the numbers, what must the other number be equal to? I'm going to give you some advice right now, and it's to avoid using y at all costs.
46 minus 1?
Right. There will come a time where we can introduce another variable, Nate. Y, if you like. But I want to avoid a second variable right from the beginning and say if these numbers add up to 46, then 46 minus x has to give you the other number. And now we can build an equation. The equation is one number times the other number has to be equal to 396.75. Let's simplify the left-hand side. I get 46x minus x squared equals 396.75. Well, okay, so this is now, everybody, the frame of mind that you find yourself in from here on in. If it's quadratic, you zero the equation. It's quadratic. Let's zero the equation. I'm going to move everything to the right side because then x squared becomes positive. So I'm adding x squared to both sides. I need to subtract 46x. And then I have plus 396.75. I never really mentioned it, but I feel as though I should. If I didn't teach this lesson the way I did, and I just gave you an equation like this, and I said, go ahead and solve it, and you thought you could rearrange for x, you're mistaken. You'll go crazy trying to rearrange for x, because there's x in one term and x squared in the other. That's not how we would solve it algebraically. What we're going to do is we're going to graph this. This is why, Nate, I didn't want to call the other number y. This is different than max-min stuff where we're interested in the value of y. We're not. So we're going to graph this function. And before we do, I need you to understand that each x-intercept is a solution. Each x-intercept is a solution. And you may think, man, he's really stressing something for no reason. There's a huge reason. Let's find the x-intercepts. X squared minus 46x plus 396.75. Did I get that number right, 396.75? Is that what it is in your handout? Okay. Now we have a problem here because I hope you understand based on the numbers, we're probably not going to see anything if we go zoom standard. So this gets a little tricky. I guess we could go to our table and start looking at, x and y. I don't think we need to complete the square. You could. I'm going to go to my table and start at 0 and go up by 1. So when I look at my table and put it on automatically, you can see that y is originally 396.75 and it starts dropping And and then it passes 0 around 12. That means there's an x-intercept over there at 12 somewhere, roughly. If I go in the other direction, y is climbing, 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 climbing. It continues to climb. Well, that kind of makes sense, everybody. Because this parabola, if there's an x-intercept around 12 and it opens up, it makes sense that the parabola is going to probably do this. So I'm guessing if we were to explore with our table, and this is a lousy situation to find ourselves in. If we could do it algebraically, we would. It'd be so much easier. But if I continue to increase for x, y decreases, decreases. Oh, it's becoming negative. Is it going to go back up? Now it's going back up again. And it's crossing 0 again, the x-axis around 34 or 35. Based on that, I'm going to put my window settings from, say, 10 to 40. Remember, it was crossing somewhere around 12 and somewhere around 35. I also am taking a mental note of some of the numbers we had. The maximum y it was getting quite big, wasn't it? 400. Does anybody remember what it went down to minimum-wise? Negative 100, negative 200? I don't remember. Not quite negative 200. So, that table is such a lifesaver. If you were just fumbling around in the dark trying to find the right window settings, you'd never hit it. All right, I would like everybody to my left to find the x-intercept on the left of your graph. I want everybody on my right to find the x-intercept, well, on your right. Everybody over here to find the x-intercept to the right. You get these two x-intercepts. Okay. Now comes the tricky part, and some of you at the end of this little explanation are going to go, oh man, it doesn't matter. What difference does it make? It will matter later. Okay. These are two solutions. They're not one solution to the problem, they're two solutions. So, solution 1 is that x is equal to 11.5. Solution 2 is that x is not 11.5, it's 34.5. So, remember we called x one of the numbers. What was the other number? What did we say the other number was? 46 minus x? Okay. So in solution 1, one of the numbers is 11.5 and the other number is this. In solution 2, one of the numbers is 34.5 and the other number is this. Are you with me on that? You're going to get 34.5 here, and here you're going to get 11.5, okay? Which means there is, in fact, only one solution because both of these solutions give us the same result. The two numbers are 11.5 and 34.5. But I want to make this point, try to anyway. What I've asterisked is the answer to the question because that's what x and 46 minus x are equal to. What I've asterisked is not the answer to the question because those are the two x-intercepts. Sometimes you'll take one of the x-intercepts or one of the solutions and it gives you a different answer than using the other one. Okay, it's pretty complicated at times. Anyway, that's your first introduction to trying to solve a word problem using a quadratic equation. Page 215, 1 to 9. I really don't care that you do every single question. If it's asking you to solve it graphically, you're just doing it on your calculator anyway. And if it ever says, I don't know if it does, solve it graphically and sketch the result, don't have to sketch the result. You need to know how to find answers to graphical solutions for quadratic equations, and there's a few word problems at the end I want you to try, okay? So you got about 10 minutes here roughly to work on this. Not really a lot of concept here in terms of putting it into practice. Find the x-intercepts, those are the solutions, of course.